last Tuesday, meeting, we were going through the definition of a bunch of different types of planar sets, right? With the goal of getting to a point where we can have appropriate generalizations of what an interval is in the real line, so that we can define differentiability of functions of a complex variable in that generalization, right? With respect to this type of planar set that we're well on our way to defining. So I think the last definition I told you is, so remember we had this long list of definitions which we'll continue today. I don't know what number we were up to.
I think we just finished 3.
Okay, yeah, right. I wanted to remind you what 3 was, the definition of an open set, right? So if every point Z of a set S, subset of the complex numbers, is an interior point of S, we then say S is open. Right, so for example, the following things. I'll make some drawings as we were doing on Tuesday, and then you tell me the inequalities that correspond to these drawings. Okay? So let's say here we have the complex plane, and I'll look at some point Z naught, and then I'll consider a circle of radius rho 1 and another circle of radius rho 2, and then I'll just look at this washer shape or flat donut. This is an open set, right? It doesn't contain any points on the edge of what I've drawn. As remember, our convention in the dashed line means it does not contain those points. If I were to take any other point here, I can find an open disk around it that is contained in the shaded region. So what's the inequality that determines this region?
You can do the modulus of Z minus rho 2 modulus minus the modulus of Z minus rho 1. Wait, actually, never mind, sorry. Just between rho 1 and rho 2.
Yeah, right, the modulus of the difference of some arbitrary...
Z naught is in between
Yeah,
rho 1 and rho 2.
right. So let's just write that down. Rho 1 is strictly less than modulus of Z minus Z naught is strictly less than rho 2. Yeah. Good. Okay. Let me take my word for it. I'm not going to draw this to scale. Here's the complex number Z, which is just equal to 3. And I'll say 5 is here and 1 is here, which is obviously not to scale, but okay. If I consider everything outside this circle, this is also an open set, right? Again, I don't contain any points that are right on the edge of the set I'm defining. What inequality does this specifies this set?
Z minus Z naught is greater than 2.
Yeah, exactly. And Z naught here is just
Yeah, Z
3,
is
right?
3.
Yeah, okay. So Z minus 3 is greater than 2, right? All the complex numbers which have distance away from 3 larger than 2. Okay. Right. So there's just a couple more. Openness is really kind of the essential topological property that we use to study planar sets. This is kind of the key feature. And in fact, if you ever get around to taking topology, you'll see that that's actually how you define what a topological space is. You specify what the open sets are. That's why we're spending a little extra time with these drawings. Okay, so here's my complex plane again, and let's say this is supposed to be a dashed line on the real axis, and I just say I look at the upper half plane, right? Not including the real axis. What's the inequality here?
The imaginary part of Z is greater than 0.
Yep. And we saw an example like this of a non-open set, right? When we looked at the real part of Z is strictly greater, or I'm sorry, greater than or equal to 0, right? Which included the imaginary axis. That's an example we did on Tuesday. Okay. Okay. Now just one more. What if let's say here's 1, here's 2. If I have this vertical strip is an open set, again, we're just not containing the edge points. Kind of the general idea of what openness is. You don't have any part of the boundary, even though we haven't defined exactly what the boundary is yet. You could probably guess, but we'll go through that in just a moment. But what's the inequality that specifies this?
1 is less than the real part of Z is less than 2.
Yeah, exactly. Not so bad. Okay. So let me just say, I'll give you an inequality. Z minus 3, if we take the modulus of that and insist that it be less than or equal to 2, a very similar picture to this, right? But what exactly do I get? I get this thing centered at 3. I get a circle of radius 2, which is filled in. It is not open. Why is that?
Because a point on the boundary wouldn't have a local neighborhood that contains only points in S.
That's right. If I take some point on the edge of the disk, on the circle, right, on the boundary, so to speak, again, we haven't defined that yet, then any neighborhood of this point, any open disk around this point, oh, sorry, I should have used dotted lines there. Any neighborhood, no matter how small we make it, will contain some points which are not included in S, the closed disk. Okay? Since it has points that do not have open disks, do not have any open disk around them entirely in S.
Couldn't you say it has points that are not interior? We were
Yeah.
talking about interiors.
Yeah, that's also a correct thing to say. I'm just spelling it out for you here. But yes. Okay. So perhaps this goes without saying, but every open disk is an open set. Okay? But since we're mathematicians, there's not really much that can go without saying. Right? I'll write this down. Okay. You can verify that for yourself, right? It's to say an open disk has only interior points, if you like. Convince yourself of that. Okay. So definition 4. Let's let W1, W2 up through Wn plus 1 be n plus 1 points in a complex plane. And for each k, let L sub k denote the line segment connecting W sub k and W sub k plus 1. Okay? Then joining together these k line segments, then the line segments join together form a continuous path from W1 to Wn plus 1. Okay? We call this a polygonal path. Okay. So, furthermore, let me say definition 5. And sorry, let's see here. We should just say this. said to be connected if for Z1 and Z2 elements of S there is a polygonal path from Z1 to Z2 lying entirely in S. Okay, so for example, what do we have here? These are all connected, all the examples that we still have on the board, right? Any point here and here, say, well, there's a trivial polygonal path, right? It contains a line that we can get to. Similarly for all these that are on the board. Let me just redraw our annulus example, or our washer example, just to demonstrate something which is not so trivially connected.
Is this for all X, for Z1 and Z2, or?
Yeah, if for every pair, I'm sorry, if that was ambiguous, I'll add that in. If for all Z1 and Z2 in S, yeah. Okay, so remember we had this annulus example. Okay, if we take some point, say Z1 here, and Z2 over on the other side, well, we just need to pick some points in between. So we can get to Z2 and stay inside S. So this is also connected. Intuitively, what this means is one piece, right? So, connected. Let's look at an example of a set which is not connected in the plane. So, I'll make a drawing first. That's actually a little high. So let's just take a circle around the origin and let me specify the set all points in the plane except for this circle. Okay? So I've just indicated a dashed line where we have points not in the set, right? So how do we specify this as some relationship of complex numbers? Let me just say, this is, let's say, point 1.
The modulus of Z minus 1, or minus, wait. No, the modulus of Z does not equal 1.
Yeah, right, we're centered at the origin.
Yeah.
Yeah, exactly, good. So this is just the set, specify the non-equality quality, modulus of Z is not equal to 1. Okay, so this is not connected. Why?
Because you can't get from a point in the interior of Z, or the interior of 1 to the...
Right, so what's the, when you're talking about this set S,
Okay, so-
everything's the interior, right?
Okay.
Yeah, so, but the intuition is correct here.
From a modulus of less than 1 to a modulus of more than 1, without crossing.
That's right, let's say, here's Z1, here's Z2. There's no polygonal path from Z1 to Z2 that does not cross this dashed line. Yeah, I mean, you're right, but we're gonna be picky about terminology, right. Since there is no polygonal path, from some choice of Z1 with modulus less than 1 and some choice of Z2 with modulus of Z2 greater than 1. So let's just add a little terminology here. Yeah.
Just making sure that thing is open.
Yeah. Yep. Right. That's a great question. Any point we pick in here, you can find an open neighborhood around, an open disk around that is entirely contained in this. We can get as close as we want. We just have to make the disk really small. Good. Okay. So let's note that. But this set is open. Okay? So openness does not imply connectedness. It's something that we deduce from this. In this example, we say that our set has two connected components. Right? That is to say, the unit disk centered at 0 and the complement of the unit disk centered at 0. Everything outside. So if we consider them separately, each of those things is connected. But when we consider them as a union, as a single set, of course neither of those sets include the boundary. So when we take their union, neither does it include the boundary. So if we have a set which is not connected, we can express it as a collection of connected components. Yeah.
If you had a set of that was all complex numbers except for their moduluses being equal to an integer, then you would have countably infinite many connected components, right?
And that's allowed. Yep. I didn't realize my pocket was unbuttoned. Okay, good. Yeah. So I told you earlier today that openness is kind of the fundamental characteristic of planar sets that we'll be concerned with. Right behind openness is connectedness. Connectedness is going to play a crucial role in our development of calculus as well. So, as such, we give these a set which is both open and connected, a special name. A set which is both open and connected is called a domain. Just terminology, not any really new content here. Okay, so here's a theorem from multivariable calculus. Okay, so and the reason I'm showing you this is to illustrate the importance of domains, or it gives you a glimpse of how this concept will be important to us. Okay, so let's suppose u of x comma y is a real valued function. Right? That is to say, it takes in a 2-vector and spits out a scalar. Defined in a domain we call it D, capital D. So if the first partial derivatives of u satisfy partial u partial x is equal to 0, which is also equal to partial u partial y. At all points of D, then u is constant in D. Okay, so this is a generalization of something from calculus 1, right? If the derivative is 0 everywhere in an interval, then that function must be constant in that interval, right? Now there's no mention of connectedness there, because we're only concerned with intervals, which are connected. So that's why we don't have to talk about this in calculus 1, because all the sets that we deal with are connected by default, right? It's just phrased in a way so that this technical detail is kind of swept under the rug. Yeah. So the reason that it's important that we say this now is because you can have a lot of variation in the way you define a planar set. Right? You can have a planar set with holes in it, right? Or yeah, basically that. And it can be, well, okay, since we're a domain, we're open and connected. That's really what this depends on. This is what you would like to be true for any open set, but you need to have connectedness as well. Okay, so let's prove this. Okay, so first of all, partial u partial x equals 0 means that u remains constant horizontal line segment. In our domain D, right? That is to say, if we restrict ourselves to a fixed value of y, a fixed value of y, and look at a line segment, we restrict ourselves to a fixed value of y, then u becomes a function of a single variable, right? And if our derivative is 0 along that line, we know our function must be constant, right? So any horizontal line segment satisfying this means that our function is constant along that line segment, right? Okay. And likewise, for partial u, partial y, equaling 0, it implies u constant on any vertical line segment. Okay. So, together, these imply that our function u is unchanged. Really, I should just say constant here. Is constant along any polygonal path in in D, with all line segments parallel to coordinate axes. Yeah? Okay. So, since D, being a domain, is connected, any 2 points have a polygonal path between them. In D. Okay, so that's great, but what guarantees that we can ensure this polygonal path has only line segments which are parallel to the coordinate axes?
Yeah, well, that's because x, y, and your third axis, x, y, and u, I guess in this case, form an orthogonal basis.
It's actually a little subtler than that. So it depends on a fact from elementary topology, which I'm going to quote you here. Okay? Let's say that any polygonal path can result in line segments parallel to the axes depends on the following. Okay. To make this statement, which is actually a key theorem of elementary topology. It's one of the first things you do. And hopefully I'll be able to incorporate a little more detail about this into the next homework. A closed line segment in a domain can be covered by a finite number of open disks. This is actually a special case of something much more general. And it's related to the notion that we'll define later today called compactness. But let me draw you a picture to show you what's going on. Okay, so let's say we have some crazy looking domain D in the complex plane where we have all these pieces cut out of it. Okay, so and of course, I made the mistake here of drawing these lines solid. Remember, our domain is open, so all these regions cut out are not contained in the domain, right? Their boundaries not contained in the domain. I was so focused on trying to recreate shapes that I was drawing that I forgot to use my convention. But actually, that stands out more when I kind of erase it a little bit. So maybe it's better, more time consuming. But okay, so here's our domain. Okay, and here's a couple points I want to join. Let's say I have Z1 here and Z2 here. Okay, so one way I could do this is choose a point here where I can take a turn. Choose a point here where I can take a turn. And then I can come up to Z2 here. Of course, let me say none of these line segments in my polygonal path are parallel to the x or y axis. So how can I generate a new path? Well, I can come out here as far as I can. So here I'll use drawn dashed lines to indicate the new path, the new polygonal path that I'm making. So I can come out here as far as I can without being able to come down and hit this line again without going into this region which is not contained in D. Okay, here's my new point. Okay, then I can do likewise. And I was lucky here, so I could actually get to a point that I used before. Okay. Actually, sorry, let me, this isn't to scale of what I drew in my notebook. I just barely miss being able to get straight up to that, so I'll just come up and then very shortly go over. Okay? So the idea is that I can basically what I'm doing when I draw these is I'm covering, say, for example, this first line segment here by an open disk here and an open disk here. Just so I miss the, here's what I'm trying to say. How do I ensure that I can always miss this region that's not contained in my domain D? Well, I just find the right sized open disk that covers a portion of this first line segment as big as I can so I don't touch that. And that's as far over as I can go. And then I drop down. And then I choose the next open disk that covers this first line segment. And that's what I can do here, right? So that's the outline of the procedure. This isn't really a proof of this fact. But if you accept this fact, it gives you a procedure for how to turn a polygonal path into a new polygonal path that has all line segments parallel to the axes, X and Y. Okay, so the more time I've spent talking about this, I will try to include this in the next homework assignment. Something that makes this a little more precise.
That would be a cool animation.
Yeah, that's true. I'm not so great with computer graphics. If you have the ability, I'd love to talk about that.
I'm sure Google does.
To animate this? I don't know if Google has that capability on its own.
Yeah, I'm sure Google has animation.
Maybe. I would say there's a lot of animations for things like linear algebra and for like more exotic topological arguments and facts. But I've never seen much animation in the way of basic topology. Maybe I just haven't been looking in the right places. But yeah, if you find anything, let me know, and maybe I'll try to take a look again. But I don't know of anything that visually represents basic topology very well. But you're right. I think it would make a cool animation.
It's just that this kind of feels like something you do in a networking class or like a computer science class because it's an algorithm defined math and something. And like those usually have a lot of animations on them because computer science.
Yeah. Yeah, so let me know if you find anything. Okay. So, right. This essentially completes our proof. So, remember I told you a square at the end of an argument is the end of a proof, right? When it's filled in, I've given you all the details. Here there's something missing, so I'll leave it open. Okay? All right. So, here's a fun problem. that kind of hinges off this theorem. Let's suppose u of xy is real value and satisfies partial u partial x is equal to 3 and partial u partial y is equal to 6. And every point in the open disk D equal to the set of complex numbers Z such that the modulus of Z is strictly less than 1. And so, when we were doing all our example drawings, I just put the inequality next to it, but if I'm actually trying to specify the set, I write this whole thing out. Okay, so what I want you to show.
When you say u of x is a real valued function, that means it returns a scalar real value.
Yep.
And but x and y, so when you say the domain is defined by a complex number,
It's taking, is that to assume that x and y are the components?
Yep. Yep. This is using the point representation of complex numbers, right? That is nothing to say we're not dealing with I in the function u. We're just scraping the data of the two real numbers
It's
off.
treating the complex number as a vector.
Yeah, exactly. We're looking at the plane, right? And we know that secretly lurking is the structure of complex multiplication. U doesn't care about that, but we are viewing it that way. Okay. Okay. Good question. So what I want you to do here is show that our function u of x comma y is equal to 3x plus 6y plus c for some constant c. Just specify, of course, this is a real number since the output of u is a real number. Without using integration. Okay. So, this is basic calc 3 with integration, right? How can we do this without using integration? Well, first let me ask you, the theorem we just proved assumed that D was a domain. This D we have is a domain, right? Because an open disk is a domain. Just a subtle point to begin with. But, just ensuring that we can actually apply the theorem that we just gave a sketch of the proof of. Okay, so what should we do? Any thoughts here? Well, I'll give you a hint. What we're going to do is use the linearity of a partial differential operator. That is to say, if we take the partial derivative with respect to x of some sum of functions that's equal to the partial derivative of each function added together, right? Okay, so the hint is we should think of some sum of functions so that we can apply the theorem that we just used, that we just proved, kind of. Okay, so let me add on to that hint.
You could assume could you assume that u of x is in some form f of x plus f of y?
Yeah, we will eventually do that.
Okay.
Yeah.
You can do that.
So yeah, I mean you can.
So from there, you could say, oh, if you assume it's in the form of f of x plus f of y, not necessarily f, but f of x plus g of y.
Oh, I'm sorry. You said that it's
Yeah.
that's. Oh no, we can't assume that.
Yeah.
I'm sorry. I thought you were just saying that we can express it as a sum of functions, not of a single variable each necessarily.
Okay.
We can't assume that with the information that we're given, and not using integration. Okay, let me give you another. Yeah.
I was going to say, so the theorem has that d, the partial derivative with respect to x and y, will equal to 0. So
Right.
trying to get that, we could say the partial derivative of u plus some other function with respect to x is equal to 0, and then the partial derivative of u plus some third function with respect to y is equal to 0, and then
Yeah.
something like that.
Yeah, that's exactly the kind of thing we want to do, right? So let me tell you how we do that. That's the right idea, 100%. So let's let v of xy be equal to 3x plus 6y. Why is that? Because then the partial derivative of v with respect to x is 3, and the partial derivative of v with respect to y is 6. In other words, it's another function, not necessarily u, which satisfies the same conditions that u satisfies. Okay? And also let w of xy be equal to the difference u of xy minus v of xy. Okay? Now, what happens when we differentiate w with respect to x and y?
Just that equal to 0.
Yeah, exactly. We get that the partials of w, the first partial derivatives, are equal to 0 for every point in our domain D. Okay? So that is to say, partial w partial x is equal to partial u partial x minus partial v partial x. We're given that this was 3, and by construction, the partial derivative of v with respect to x is 3, 0, and then likewise for y. Oh, sorry, y, not x. 6 minus 6 for all points in D. Okay, so this implies by our theorem that the function w x y is equal to some constant c in D, which implies that u of xy is equal to v of xy plus c, or 3x plus 6y plus c. Okay? So, a bit of a trick there. Kind of cool. So let's go back to making a few more definitions about planar sets. And then after we finish that, we'll get to talk about the Riemann sphere and stereographic projection, which is maybe a little less dry. Right? This is a lot of definitions. We do get to look at pictures, but it is a lot of just like, here's a thing, here's a thing, here's another thing. Okay, so here's another set of definitions. Z naught is a boundary point of S, a subset of the complex plane, if every neighborhood of Z naught contains at least one point of, or I guess I should say in S, and at least 1 point not in S. In S. Okay. I think we're probably pretty comfortable with this, right? We were talking about like on the disk, the open disk. You know, the part that's not included on the edge is a boundary point. Okay, so I think this is probably the most common confusion in the first month of elementary topology. A boundary point of S need not be contained in S. Even though it is related to S somehow, it's a point that's related to S, it may or may not be contained in S. So let me write that down. Caution. A boundary point of S need not be contained in S. Okay, just really quickly. Here's a set S, an open disk. Here's a boundary point of this set S equal to the complex numbers which form an open disk around Z naught. Z1 a boundary point. Wait, I'm forgetting a right? Boundary point of S. But Z1 is not contained in S. Okay? By contrast, let's say I specify some set R by the open disk around W naught, which has radius tau. Here's W naught. Sorry, less than or equal to tau. Here's some point W1. W1, a boundary point. R, and W1 is an element of R, right? Okay, so just keep that in mind when you're dealing with boundary. The boundary is kind of a tricky thing to get a hold of working with, but you know, once you have this kind of picture in your mind, it becomes a little bit easier. Okay? Good. So, a couple more definitions. A set of all boundary points of S is called, unsurprisingly, the boundary or frontier. Of S. We sometimes write BD of S for boundary. That's not in our textbook, but you will see that in some textbooks.
I've seen like the partial derivative symbol.
Yeah, that's another thing that you'll see, especially when you're doing topology, or you even see it a couple times in Calc 3. Why don't we say, that's good to note. Or you might see the boundary of S. This is another use of a lowercase delta drawn in this way, besides partial derivative. Right. We will have infrequent occasion to talk about partial derivatives, so I'm going to try to avoid this notation, but you might see it in the textbook. Thank you for pointing that out. Good. So, right. Let me okay, so let me just say this. Notice that since an open set has only interior points, it cannot contain any of its boundary points. Okay, this is another way of getting at a characterization of what it means to be open. It can't contain any of your boundary points. Okay, so there's a somewhat complementary notion to an open set, which is that of a closed set. And I bet that you can guess what the definition of a closed set is. Anybody want to take a stab at that? Yeah.
Set that is not open.
Ah, careful. Right, that's why I said it's a little misleading because we can have sets which are neither open nor closed. Right? Think back to Calc 1. Right?
Oh, yeah.
Because it contains one of its endpoints, but not the other. That is, it contains a boundary point, so it's not open. But it does not contain all of its boundary points, which is the definition of closed, having to contain all your boundary points.
I have a friend in group theory right now.
Mhm.
They're talking about closed and open sets.
Right, a set can be simultaneously open and closed. Think of an example. Anybody think of an example? Now that's tricky. That can be satisfied in certain things. There's a couple simpler examples though.
Empty set.
The empty set. Great. Very good. Let me tell you the definition of closed, and then we'll talk about why the empty set is both open and closed.
Is closed the union of an open set and its boundary? Set.
That's a theorem. It's not the definition, but yeah. Yeah. Good. Okay, so this definition 3 in this series of definitions. S is said to be closed if it contains all its boundary points. Okay, so e.g. the empty set, a subset of complex numbers, is both open and closed. Okay, how do we show that the empty set is open?
Could you say that because it has no points, every point that exists is an interior point? Can you?
That's really close, right? So what's the definition of open? Every point of the set is an interior point. Since there are no points, that condition is satisfied vacuously, is what you're saying. Yeah, and that's almost exactly what you're saying, right? But you don't say that any point is an interior point because there are no points. Right? That's kind of a pedantic thing that I'm saying here, but yeah, the point is that there's no points, right? Okay. Open, since every point none is an interior point. Okay. How about closed? Closed, since what is the boundary point of the empty set?
The empty set? Nothing?
So right, there are no boundary points, right? Because in order to be a boundary point, any neighborhood of that point must contain at least one point that's in our set, and at least one point that is not in our set. Any neighborhood of any point cannot contain a point in the empty set because there are no points in the empty set. Okay? And closed, since it has no boundary points. And therefore contains all its boundary points. None. Okay. So, think about this at home. C is both open and closed. It's a similar kind of easy to verify but hard to say type of thing. Okay. Now, just a side note related to group theory. We're talking about the topology of the complex numbers in our setting, right? The topology you put on a group is much different in character. So there are the possibility of having many more types of sets that are both open and closed. And so it's more meaningful in the context of group theory to talk about sets which are both open and closed. But in fact, check me on this, but I think if you're dealing with a connected space, I'm saying something slightly more general than just for complex numbers. If you have a connected space, the only subsets of that space, which are both open and closed, are the entire space and the empty set. These are the prototypical examples. But the topology you put on a group is most often does not make it connected. Okay? Unless, of course, you start studying Lie groups, in which you insist that they're connected, because then you can do more cool topological things with them. Okay, so I'm just giving you a lot of stuff that might not make sense, but you know, it's like mathematical culture. You might be interested in reading more about this in your free time or something. Okay? Yeah, this isn't going to be on the test, is what I need to say. Okay, so where are we here? I think we just have a couple more definitions. Oh yeah, so I gave you an example in the real numbers of a set which is neither open nor closed. I guess we should talk about a set of complex numbers which is neither open nor closed. So let's look at the set S, defined as the set of complex numbers such that 0 is strictly less than the modulus of z, which is less than or equal to 1, is neither open nor closed. Why is this? Well, it definitely contains all the boundary points on the outer ring, the outer circle, right? The complex numbers of modulus 1. But it does not contain 0. So that's a boundary point that it does not contain, right? sorry.
How would 0 be a boundary?
That's, yeah, I just said a false thing.
Okay.
0 is not a boundary point. Let me modify this example slightly. That set S that I wrote down in the first place will become important to us, the punctured disk. But it's not apt for this example. Let me just look at an annulus. Okay, so I contain some boundary points, but not all. That makes me neither open nor closed, right? Because if I'm closed, I have to contain all my boundary points. So if there are boundary points I don't contain, I'm not closed. And as we discussed, an open set cannot contain any of its boundary points. So if I contain any of my boundary points, I'm not open. Okay. Good. Right. So let me call the set S equal to a set of complex numbers such that Z minus Z naught is less than or equal to rho. The closed disk centered at rho, centered at, sorry, Z naught with radius rho. You can verify that this set is closed, right? And again, just like we have common occasion to talk about open disks, so will we have nearly as much occasion to talk about closed disks. Okay, so last couple definitions, I swear, for a while. Right, so what was I up to? 4. The subset S of C is said to be bounded. If there exists a positive real number R, such that the modulus of Z is strictly less than R for all Z contained in S. That is to say, S is contained in some neighborhood of the origin. Okay, so this makes a type of sense, right? This terminology, because it's saying that we can that the set S we're considering is finite in some way. That we can just put a ball around it and actually contain it in a single finite thing. Okay? Assuming R is a finite real number. Okay. Otherwise, S is unbounded. Okay, what's an example of an unbounded set?
All complex numbers.
All complex numbers, yeah, exactly. There's no finite unit disk centered at the origin that contains all complex numbers, you can always come up with a complex number of a larger modulus than any real number r, right? Any other examples that we drew on the board today or Tuesday? Unbounded.
Well, like the real part of Z being greater than constant.
Yeah. Right, any half plane, for example, right? That is to say, let's say the real part, Z is strictly greater than 1, unbounded, right? Good. Even more restrictive, right? The strip is unbounded because it extends infinitely in the imaginary dimension in both directions, right? Okay. Yeah.
Would the empty set be bounded?
Interesting question. Is the empty set bounded? So, let's see. Yes. Because it's bounded, and any choice of R will do. Because there is no point to take the modulus of.
I wasn't sure if that was going to be like anything's fine or nothing works because there's no way to like compare because there's no points to take the modulus of.
Yeah. So I think you could actually go either way, but the convention is to say that it's bounded.
Okay.
Yeah, that's a good question. But yeah, we'll assume that the empty set is bounded. In fact, I don't think I've ever seen the opposite convention. But you could make that. That is something that's particularly useful. And we'll have no occasion to talk about the boundedness or unboundedness of the empty set. But yeah, the convention is bounded. Okay, great. That covers everything we need to know. Oh yeah, sorry, did you have a question? I thought you were raising your hand, sorry. So that covers everything we need to know for the time being about planar sets. So now, we're going to talk about one final geometric interpretation of the complex numbers, this time in terms of how they sit in three-dimensional space and how they relate to a sphere. Okay?
Yeah, this one unrelated question. I guess not related, but in Calc 3, there were different theorems we used, and that we covered in the vector calculus unit relating to open and closed boundaries and domains. Sorry, not boundaries, but like domains. Is there going to be something analogous in complex numbers?
Yeah, right. So this is how we'll, if you think back to the beginning of our discussion about planar sets on Tuesday, the reason we made all these definitions is that we will formulate the results, the generalizations of calculus to a complex variable for functions defined in domains, right? And we'll use those characteristics of openness and connectedness in the proofs of those facts that we want to extend from calculus to complex variables.
Sure.
Yeah. Does that make sense?
Yeah, that's
Okay, great. Okay. So, I want to tell you about the Riemann sphere and stereographic projection. begin by considering the unit sphere in R3. Which has an equation x1 squared plus x2 squared plus x3 squared equal to 1. Okay, so right away you might ask yourself, why did I choose the variable names x1, x2, and x3? Because I'm going to reserve x, y, and z for how I deal with the complex numbers, as we've been doing consistently up to this point. Also, we won't be talking about three-dimensional things very often, so I take this slightly less conventional notation for the time being. Okay, so let me draw this sphere. See if I can draw this sphere. It's not so bad. Okay, maybe more of an onion than a sphere. And let me also draw in this diagram an equatorial plane. And so that is to say I'm cutting the sphere. We're centered at the origin, right? So I want to say that I have my origin here, 0, 0, 0, and basically this is the XY plane, right? Or sorry, the X1, X2 plane. Okay, meaning it contains the origin. Okay, so what I would like to do is associate to each complex number a point on this sphere. We want to associate to each complex number a point on this sphere. Okay, so and not just any point, a unique point on this sphere. Okay. To do this, we'll use stereographic projection. Here's how we do that. What I mean by that. We'll choose a point. Point choose N, the North Pole. Now I'll refer back to my picture here. Maybe it's kind of nice that I drew it more onion shaped. Here's my point N, which I'm going to fix. Okay? And fix it. Then what I'm going to do is associate the x1, x2 plane, this equatorial plane, with the complex numbers. Associate the x1, x2 plane with the complex numbers, or the complex plane. C. Then a complex number z, little z, can be written, or sorry, I'll say written in our standard way, x plus iy, can also be represented in 3 space on the plane, on the x1, x2 plane, as x, y, 0. Okay, I'm just tacking on an additional 0 to say that the x1, x2 plane is what I'm considering as the complex numbers in 3 space. Okay, so I'm still not on the sphere, but I have a representation in 3 space of the complex plane. How do I get a unique point on the sphere associated to this z?
Square root of 1 minus x squared plus y squared minus y squared.
Yeah, so you're trying to develop a formula for
Yeah.
how to do that. I have a hard time parsing equations when they're said.
Okay.
What you said sounds close to right, but let's think about geometrically how we arrive at that point. And then we will derive the formula from that, but yeah.
You could make a triangle between the point on the complex plane, the n that we've defined, and whatever whatever z value is going to be on the circle at that vertical one.
So yeah, actually the first step is just enough. What you want to do is, okay, so let's say I have this point little z here, x, y, 0. All I want to do is draw the line from n to little z, and that will intersect my circle, my sphere, at some point big Z. Okay, so then, okay, we take this 3-dimensional representation of little z, and we associate that, and associate it with capital Z, the point of intersection of the line through with the sphere. Okay? So,
Does that mean that the points on the x1, x2 plane inside the sphere define all the points on the part of the sphere below that plane, and then every point outside of it, like infinitely, is the top half of the sphere?
yeah, exactly. Good observation. So the northern hemisphere, the half of the sphere above this plane that I used to cut, corresponds to all the complex numbers which have modulus greater than 1. Right? And the southern hemisphere corresponds to all the complex numbers that have modulus less than 1. Right? And the complex numbers which have modulus exactly 1 is just this great circle of the sphere that actually lies on the plane. Good. Great observation. Okay, so let me just say, give credit where credit's due here. So we can do this procedure without thinking about complex numbers, right? With just the x1, x2 plane. But when we think about C and stereographic projection, we call the sphere the Riemann sphere. And he's the first one to use this technique of stereographic projection to represent the complex numbers. So we're almost out of time, but just a historical note. Stereographic projection, this process of assigning a unique point on the sphere to a point in some plane, or vice versa, it comes from cartography. This is from people trying to make maps of the globe. Okay, so it predates Riemann, this whole process, but he's the one who applied it to representing the complex numbers as points on the sphere. Okay, so we're going to develop a formula for C and talk about some of the nice properties that certain geometric objects have in the plane corresponding to certain geometric objects and how they intersect with this sphere. Okay, and that's what we'll pick up on Tuesday. Have a great weekend. Oh yeah, you might have noticed I didn't post a homework assignment. I decided that I'm just going to give us a little more time before, so we have, because you know I've only really thought of like 3 good problems yet, so I want to make it fun for you. Okay, so have a good weekend, and I'll see you on Tuesday.